The chemical bond has been an academic curiosity for well over 100 years, and with good reason. Why atoms bond to one another is one of the most fundamental concepts required to understand the universe around us. From Lewis and his famous dot structures to modern quantum mechanical formulations of the bond, all of these are meant to help us understand something that is so intangible. In fact, chemical bonds have even been compared to the mythical unicorn, owing to the fact that everyone supposedly knows what they look like, despite no one ever having seen one. The truth is that the chemical bond deserves a course all unto itself, but for us, we'll focus on a brief survey of the most important aspects of chemical bonding that will help you understand a great deal about how chemical species behave. There are actually two different models of the chemical bond I'd like to discuss. Neither is perfect, and yet neither is entirely incorrect either. They are complementary viewpoints that find utility in many branches of chemistry, and they will help you make sense of a plethora of phenomena in your everyday lives. Like, why are trans fats so bad for you? Why do some objects glow under a black light? Why are greenhouse gases like CO2 bad for the environment? Why do we even see colors? All of these, and so much more, require us to understand models of the chemical bond. The first model we'll start with is known as valence bond theory. Let me start off by introducing you to a problem. But the way I want to start is by thinking about what a bond actually is. And most, if not all, of my discussion today will be framed by what's called valence bond theory. That's really the theme for today. And in valence bond theory, among many other thought processes, a bond is really a coming together of two atoms. And we all have been thinking about bonds as being a sharing of electrons. And so if we think about how atoms might share electrons, recalling that those electrons live in orbitals, let's first think about something simple like H2. Hydrogen has an electron, and that electron, at least in its ground state, exists in a 1s orbital, which is spherically symmetric. And so as two hydrogen atoms would approach one another, their electronic orbitals would eventually overlap, and we would have this region of overlap. And it's a useful idea to think of that overlap region as being what a bond actually is. And valence bond theory, which is again our theme for today, has a name for this overlap. It's called a sigma bond, and we would call that sigma overlap of a couple of different orbitals. So this sigma bond is a relatively simple thing to think about, and it also gels with our understanding of what a covalent bond actually is, right? It's a sharing of electrons where, in most cases, not all, but in most cases, one atom comes along with an electron and a second atom comes along with an electron, and when they get together, they share those electrons. And from an orbital perspective, we can think of the sharing of those electrons as being the overlap of those two orbitals, the overlap of those two regions of space. And that's useful, except that it, I think, introduces a lot of problems for us. And let me demonstrate what I mean by that with a relatively simple example. Imagine the beryllium F2 molecule, so just BeF2. We have a lot of tools that we've developed so far in this class. We could do a Lewis structure for this molecule. Wouldn't take a whole lot of effort. We would know that there had to be two fluorine atoms bonded to the central beryllium. If we counted all of our electrons, we could distribute the remaining ones around the fluorine atoms, like so. And this is what we would be left with. And then we could go one step further and actually think about this from a VSEPR model, which would confirm to us that we would certainly expect the angle here to be 180 degrees. That's the best way to keep the two electron domains that beryllium has in its vicinity as far away as possible from each other. So we've got this notion of electrons and bonding being the sharing of electrons between neighboring atoms. And we know from Vesper that these domains would likely be 180 degrees away from each other. And this can all be experimentally verified. But if we were to also imagine, as I think we should, how to connect the various topics we've learned about in this class, we could also recall something like an electron configuration and an orbital energy level diagram. What is the configuration for this central atom? Well, beryllium is in the second row of the periodic table. It's got 1s2, 2s2. Relatively simple system, so this is a good starting point. If I were to draw its orbital energy level diagram, as I often do, starting only with the valence, and there's a good reason for that. We're talking about bonding today, and bonding happens with the outermost electrons of elements. So the outermost electrons would be the ones that would be involved in bonding. They're the ones we should be talking about, and those outermost electrons are, of course, the valence. And if I thought about all of the valence orbitals, I would have to recall, of course, that there are also 2p orbitals, although in this case, not populated or empty. And herein lies the problem that I think and I hope that you see. According to my orbital energy level diagram, beryllium is actually satisfied. It's got 2 electrons, but both are paired, and though they're in an s orbital. So really there's 2 problems here. One is, why should beryllium bond at all, at least not with 2 things? And if it does, how can I expect beryllium to hold those bonds 180 degrees away from one another, when in reality none of these orbitals, even if we were to use the 2p orbitals, none of them are 180 degrees away from one another. The p orbitals are, of course, mutually orthogonal. They're all 90 degrees away from one another. So we've got an issue here. Our atomic orbital energy level diagram and electron configurations don't seem to gel very well with our notion of Lewis structures and Vesper. And this is really the job of valence bond theory, which is the model we're talking about today. We're meant to fix this issue. We're meant to reconcile these 2 notions that seem at odds with one another right now. Okay? And so what valence bond theory does, and really the central tenet of valence bond theory, is it introduces a concept known as hybrid atomic orbitals. Now, what is a hybrid atomic orbital? Well, first of all, let's be clear. It is not an intuitive or an obvious thing for us to do. It is a human invention, specifically for the purpose of reconciling this problem that we have here. We have a lot of evidence to suggest that this is true, and we have a lot of evidence to suggest that this is true. What we need is a theoretical framework that joins both of those so that they can both be true simultaneously. And valence bond theory gives us hybrid atomic orbitals to achieve just that. Now, the way we do this is by looking at how many electron domains is it that we need to satisfy for the particular central atom that we have. In this case, it's beryllium, and in this case, it's 2 electron domains. So what I'd like to do today is I'd like to reconcile this problem, but of course, I'd also like to think about 3 electron domains and 4 electron domains and others, so that we have a comprehensive understanding of how valence bond theory works. So, what is a hybrid atomic orbital? A hybrid atomic orbital is actually a mix of the usual or normal atomic orbitals that we've been dealing with since day 1 of this class. We know about the 2s and the 2p set of orbitals, but what we don't yet know about are the hybrids that we could create from those if we wanted to. Again, not an intuitive or obvious thing to do at this point, but let's just try it and see what we get. We first look at the Lewis structure we have here and note that we need 2 electron domains. That's our first signal that we need to create 2 atomic orbital hybrids. And how we do that is we come over to our electron energy diagram and we take the first 2 atomic orbitals in the list, and these are the ones that we are going to create hybrids from. What we're proposing is that by mixing together this s and this p orbital, we are going to get two brand new orbitals at an intermediate energy. And of course, we would still be left with the same old 2p orbitals that we haven't touched yet, these ones right here. But these two new orbitals I would get by literally mixing this s with this p and getting two brand new ones. Let's first name these new orbitals. Because I've mixed an s orbital with a p orbital, I'll call them sp hybrids. And so these are hybrid atomic orbitals. And if I realize that, of course, I have two electrons in this particular system, I have a scenario here where I have two unpaired electrons now, because I have no reason not to fill these both singly before I pair them. And that is a scenario ripe for creating two bonds. So I can tell that I'm probably going in the right direction. But the question is, what would those sp hybrids look like? What does it look like to mix a sphere with a dumbbell type shape that is the p orbital? Here is a diagram that's meant to help us with this question. This is an exercise that can be solved geometrically or mathematically, but it is true nonetheless that if I take a p orbital and mix it with an s orbital, I can create two hybrids. And I get those two hybrids by combining them in a positive way, by adding them together, or by subtracting them. And I can get this version, and I can also get this version. Notice that this sphere is essentially amplifying one side of this p in one case and amplifying the other side of the p orbital in the other case. And this is realistically what happens. We won't go through the math for how to actually determine this, but the point is, if we take these two orbitals, an s and a p, combining them creates these two sp hybrids. And if I superimpose these onto the same nucleus, as of course they would be in a real molecule, we see the result, which is that a single sp hybrid points to the left and a single additional sp hybrid points to the right. Miraculously, 180 degrees away. In other words, we have captured the realistic structure that we would expect if we had to bond two things, or if we had two electron domains that we had to distribute linearly, as we know they would be. Two hybrids created from an s and a p orbital produces exactly that geometry. Now remember, what you're looking at here on the right are two independent orbitals. One of the sp hybrids indicated here on the left, and the other sp hybrid indicated on the right. So what this means is that we've got a scenario where our beryllium atom can now bond with two separate atoms at an angle of 180 degrees. That is now reconciled with its atomic orbitals because we've created hybrids out of those atomic orbitals. And the hybrids are, in fact, 180 degrees from each other and contain only a single electron. Therefore, they're able to share that electron with their neighbor. In other words, we've created a scenario that has an ability to bond with two separate things and both being 180 degrees away from each other. So this is really the strength of valence bond theory. It creates hybrid atomic orbitals from the usual atomic orbitals to reconcile the notion of the bonds that we know to exist. Now, I get questions very often from students on this topic. It's generally a new topic for students at this point in their chemistry studies. And the question is almost invariably around, why would an atom do this? And I want to be really clear that it's not necessarily the atom that's doing this. The atom does not exist in this hybridized state. Beryllium atoms don't go around flying in space deciding to hybridize into this sp hybrid state. This sp hybrid state is a theoretical invention that helps us explain the existence of these bonds. Another way to think of that is that the beryllium atom would never be locked into this sort of a configuration, it would only hybridize, if you will, for the purpose of creating a bond. A bond is a stable thing. A bond is something that matter generally likes to make. Matter becomes more stable when it's bonded together in many instances. And so this, while not favorable to hybridize these orbitals for the purpose of hybridizing them, it is favorable to create this scenario so that we can create this scenario, so that we can bond. So how does this apply to other numbers of electron domains? Let's think about a molecule like, for example, BH3. We've seen BH3 in other contexts and in Lewis structure diagrams. And if you were to draw the Lewis structure for this molecule, you would undoubtedly come up with the following. And you would decide that because this molecule had 3 electron domains, 1, 2, 3, that it would be a trigonal planar structure. In other words, the angle formed between the bonds here would be 120 degrees, exactly. Now, the question still remains, if we visit the electron configuration for the central atom boron, again, looking at the periodic table, we know that it would be 1s2, 2s2, and it would have a single electron in the 2p set of orbitals. And if I were to draw an energy level diagram for the valence atomic orbitals here, as I did before, again indicating that this is energy, schematically, I would have this, and of course, I would put my electrons in it, and this would be the representation of boron. And here we see the exact same problem. In fact, you will notice this problem in almost any structure you ever draw. The atomic orbitals of the central atom rarely, if ever, reconcile the reality of the molecular structure. In other words, it looks like boron can only make one bond, doesn't it? And it looks like that bond, certainly any other bonds, would not be 120 degrees from each other. All of the orbital ingredients that we have here to create bonds are all mutually orthogonal at 90 degrees. Again, no way to create this structure, unless, again, valence bond theory comes to the rescue with its hybrid atomic orbitals. So let's go through the same process we did for BEF2. First, we count the number of domains we need to accommodate. That's 3 in this case. And this is the same number of electron domains we thought about back when we talked about Vesper. So again, we have 3 electron domains here that we need to accommodate. So the strategy will be to hybridize 3 atomic orbitals. Starting with the s, that's 1, we need to capture 2 more. So we will capture those orbitals to hybridize them, and we will create always as many hybrids as atomic orbitals that went in. So we hybridized this s orbital, this p orbital, and this p orbital to create 3 new ones, which we will call sp2, for reasons that we've got a single s orbital and 2 p orbitals. Therefore, we call them sp2. So these are sp2 hybridized atomic orbitals. And let's not forget that we have the leftover 2p orbital that we've not yet touched. That's just brought back over here. We still have 3 electrons, so of course we can place those in our diagram. And lo and behold, look at what we have now. We have a scenario where we have 3 electrons, all able to be bonded because they're all unpaired and can create a bond and share with some other chemical species. And they are sp2 hybrids. So the question remains, of course, like before, what does an sp2 hybrid look like? Here is a diagram indicating exactly that. If I take an s orbital and 2 p orbitals, which necessarily will be at 90 degrees from one another, again, geometrically, mathematically, as these shapes mix, what they will create are 3 hybrid orbitals pointing, you guessed it, 120 degrees away from one another. And the reason why this is able to work out this way has to do with the direction of these lobes, as well as the sign of the function that determines these lobes. And what they do is they add in favorable or unfavorable ways in various directions. And what you will get are orbitals pointing in each of the three corners of a triangle. In other words, our three atomic orbitals produce, as they mix, three equivalent sp2 hybrids, each with a large lobe pointing toward the corner of a triangle, each producing a structure that allows these lobes to be exactly 120 degrees away from each other. So again, recall that this image shows three separate sp2 hybrid orbitals all superimposed onto the same nucleus. And remember that in our case of BH3, each one of these has an electron located in it. And therefore, we can easily accommodate the structure of BH3. And in that structure, recall that I'll have a hydrogen atom with an s orbital here, a hydrogen atom with an s orbital here, and a third hydrogen atom with an s orbital there. And the overlap created between the hydrogen S and the boron sp2 hybrid will allow me to create three independent sigma bonds. So the diagram is not all that clean, but you can see that I've got overlap here. So this is a sigma bond between boron and hydrogen. I've got overlap here, creating another sigma bond, and overlap here, creating three independent sigma bonds. And in general, when you see single bonds in a Lewis structure, a valence bond interpretation of those suggests that these are sigma bonds made from hybrid atomic orbitals. Let's quickly move on to the case of 4 electron domains. A prototypical case here would, of course, be methane. We talk about methane often when we think about these types of systems. And you've seen the Lewis structure for methane. Of course, it has 4 domains to accommodate all 4 hydrogen atoms. And this is a tetrahedral molecule, which is difficult to indicate on this two-dimensional screen. But you can all recall that what that means is that the angle between any 2 adjacent domains is 109.5 degrees. Recall that this sort of looked like a tripod, if you will, with one sticking up from it. It's a very symmetrical structure, but again, if I go through the process of asking myself, what is the electron configuration for this carbon atom, I would discover that it is like so. And if I translate that to an energy level diagram, again, just for the valence atomic orbitals, I will realize that I have a confusing scenario here where it looks as though carbon can only create 2 bonds. And it looks like those 2 bonds should be at 90 degrees from each other. Exactly the same problem I've been repeating over and over again, which luckily has exactly the same solution that I've been repeating over again. And these are the hybrid atomic orbitals for these systems, so hybrid AOs. How do we do this? Well, the rules are exactly the same. You first count how many electron domains do we need to accommodate. In this case, it is, of course, 4, which means that we need to hybridize 4 atomic orbitals. Starting at the lowest energy orbital of the valence set, that means I need to actually capture all of them. All of these will create 4 hybrid atomic orbitals, and so I can indicate that on a diagram here, and they will all be equivalent because that's the point, and the name of them would be associated with the ingredients that went in. An S and 3 Ps would therefore correspond to sp3. So I would say that these are 4 equivalent sp3 orbitals, and if I were to put my electrons into here, which I don't necessarily have to do, but there they are, I see that I've got 4 electrons all available for bonding. The question remains, again, is what do these sp3 orbitals look like? And again, here is our diagram that indicates that. We've got our 4 ingredients, right? The s orbital and each of the 3 p's, and I've indicated the Cartesian axes here for each of those, and we can see that they all point 90 degrees away from each other. But again, geometrically speaking, as we combine these and these various perpendicular directions combine in the various combinations that they can, what is produced are these 4 sp3 hybrids. Notice that they each point to the corner of a tetrahedron. In other words, we get a fully tetrahedral arrangement. The large lobes of each of these sp3 hybrids is exactly 109.5 degrees away from each other. And again, the mathematics of how these combine to produce these is beyond the scope of this class, but the logic is sound, and that is that as I mix and match these orbitals that point in various directions, what I create are these hybrids. And again, these hybrids have a large lobe and a small lobe, which has to do with the fact that this S tends to combine favorably with one half of those P's and unfavorably with the other half. Again, the result here are 4 equivalent sp3 hybrids pointing in a tetrahedral direction. And so for the case of methane, again, we can remember that I'll have a hydrogen 1s orbital overlapping with each of these sp3 hybrids to again create 4 sigma bonds in each one of these places of overlap here. And so that's really how we explain the bonding in something like methane. And in really most chemical structures can be thought of in this valence bond type way. You count up the number of domains you have, and then you create that number of hybrid atomic orbitals from the usual or normal atomic orbitals to create the hybrids. Now this works for all kinds of other systems, even systems that have many more bonds in them, or at least some more bonds in them. Structures like PCl5, for example, which actually breaks the octet rule. What would I be dealing with PCl5? Well, it would be a very similar scenario, but recall that phosphorus, of course, is in the 3rd row of the periodic table, and therefore its valence would be 3s, 3p, and don't forget it would have 3d available orbitals for it as well. Phosphorus, of course, has 5 valence electrons, 1, 2, 3, 4, 5. And again, you would say to yourself, well, maybe it should only make 3 bonds, but of course this molecule exists. PCl5 will of course have 5 electron domains in its vicinity, so in order to create that scenario, we'll need to mix and match 5 orbitals, which will actually cost us one of those Ds. We're going to need that one to create a set of 5 equivalent hybrids. So if I mix and match, and let me just make my diagram a little bit clearer by leaving those 3d orbitals there untouched, what I will get are 5 equivalent sp3d orbitals now, right? So the logic is very much the same regardless of which molecules we go to. And now I've got a scenario where my phosphorus atom is able to bond to 5 things in an equivalent way. And although we're not going to go into much detail with all of these domains, my point is only to illustrate to you that this is generally applicable, almost universally, to any chemical species. We can think about its bonds anyway, in terms of a hybrid atomic orbital approach. And this is the crux of valence bond theory.